Hello everyone. For this tutorial video, I'd like to discuss the Taylor and Maclaurin series, and give a proof of why it is the way it is. If we use an example function to work with, such as 1 over 1 minus x, which is relatively easy because it follows the geometric formula, and then next assume that the function will have a power series representation around x exactly equals to a, then it follows that every term in the power series except the coefficient of point 0 cancels out, so the function at point A is simply the coefficient of the first term, or 0th term more technically. We see by similar reasoning, the derivative at this point must be the coefficient of the next term. The derivative after that is 2 times the coefficient of the term after that, and so on. With some clever rearranging, we can see that the coefficient of the third term, or second term more technically, is the second derivative of x equals a over 2, and then the coefficient of the term after that is the next derivative, or third derivative, divided by the order of the derivative, so 3, times the 2 we found earlier. It follows then that the coefficient of the next term would be the derivative of that, divided by the order of the derivative times everything we have found so far. So in conclusion, provided that x equals a, we can see that every coefficient is the nth derivative of the point x equals a divided by n factorial, where we remember factorial is every positive integer multiplied up to that point, i.e. 4 factorial is 1 times 2 times 3 times 4. In conclusion, if and only if we can find a power series for the function in general, and the power series is also valid at x equals a, then we can simplify it with a formula for the Taylor series, which is the infinite sum of nth order derivative at the point x equals a over n factorial times x minus a raised to the power of n. There's another type of series called the Maclaurin series, which is simply a specialized type of Taylor series, where we assume x and a are both the value 0. Which means we have the same general formula, but now x minus a simplifies to x raised to the power of n. So now that we have figured out what a Taylor series is, and given a proof of why exactly it works, we can find the Taylor series for specific functions, such as e to the power of x around x equals 0. We remember the nth order derivative of e to the power of x is always e to the power of x. It stays the same no matter how many times you differentiate it. So it follows the nth order derivative at point 0 must always be e to the power of 0, because it is e to the power of x for any x value, and e to the power of 0 is 1. In conclusion, we have 1 in the numerator and n in the denominator, but we can actually simplify this further by multiplying the 1 by the power part, or x to the power of n. And that is our final answer for how to represent e to the power of x at x equals 0 with a series. Now that we have figured out how to represent functions with infinite sums, we can state, before we officially conclude the video, that this series can be used to approximate any function using nothing but polynomials, as the number of polynomials we add get closer and closer to infinity. And that is the magic of how Taylor series works. As long as x equals a, so we draw all polynomials relative to this point, and as long as we know that a power series representation for the function exists, which will not always be true for every single function out there. Now that we have discussed thoroughly everything about series, we can wrap up our discussions on Calculus 2, and move on to the final, most difficult type of calculus, which is calculus of 3-dimensional graphs rather than 2-dimensional, so where we have z as a function of x and y at the same time, rather than y as a function of x. And this is officially called Calculus 3, rather than something like 3D calculus. Don't forget to subscribe if you found this video informative, and make sure to see other tutorial videos, and follow me on either Facebook or Twitter for more content.